Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module we are discussing Valence bond theory VBT. The contents of this module are: there is an introduction to valence bond theory, orbital overlap and conditions for effective overlap, sigma and pi bonds, formation of hydrogen molecule, and concept of resonance. First of all, introduction to valence bond theory. You know the basic theory like Lewis theory about covalent bond. But the Lewis theory can have several drawbacks. It cannot explain many things associated with a covalent bond as well as a covalent molecule. It cannot explain the strength of a covalent bond, the bond length, the shape of the molecules, etc. In order to explain the shape of the covalent molecules, the concept of resonance, etc., and higher aspects of the molecules which are connected by covalent bond, we require some important theories, out of which the most important theory is the valence bond theory. Now we can enter into some introductory aspects of the valence bond theory. Quantum chemistry or quantum mechanics explains theoretically the structure, bonding and reactivity in chemical entities. The chemical bonding in molecules is explained quantum mechanically via two popular theories. The two popular theories are: number one, valence bond theory VBT and molecular orbital theory abbreviated as MOT. Valence bond theory was developed by W. Hitler and F. London in the year 1928 and later by J.C. Slater and Linus Pauling. Molecular orbital theory was developed by F. Hunt, R.S. Mulliken and J.E. Leonard Jones between the years 1927 to 1932. Both these methods, that is valence bond theory as well as molecular orbital theory, are based on assumptions and have different physical interpretations. This simply implies that the valence bond theory and molecular orbital theory have different physical interpretations and different concepts. Out of these two theories, we are giving emphasis to valence bond theory in the present module. In valence bond theory, a discussion of the valence bond theory is based on first parameter, the knowledge of atomic orbitals, electronic configuration of elements, the overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principle of variation and superposition. It should be noted that these are the important basis of the valence bond theory VBT. Now, a covalent bond forms when the orbitals of two atoms overlap and are occupied by a pair of electrons that have the highest probability of being located between the nucleus. Here there is a term called probability. Probability means the possibility. That is, during the formation of a covalent bond by the sharing of electrons, the shared pair of electron most likely to be present in between the atoms. That is, high probability of finding that paired electrons in between the atoms. A set of overlapping orbitals has maximum 2 electrons that must have opposite spin. We know the basics of the covalent bond formation, that during the formation of a covalent bond, there occur some overlapping of atomic orbitals. During the overlapping of atomic orbitals, electron pairing also happens. That is, half-filled atomic orbitals undergo overlapping to form a covalent bond. During the formation of a covalent bond, the orbitals, the half-filled orbitals with the opposite spin come together, overlap together, and a single bond or a bond or a covalent bond is produced. The greater the orbital overlap, the stronger or more stable will be the covalent bond. that is, the extent of overlap has strong connection with the strength of the resultant covalent bond. This is one of the most important aspect of the valence bond theory, which govern the strength of the covalent bond produced. This strength of a covalent bond cannot be explained on the basis of the Lewis theory. This is the most important advantage of the valence bond theory, which can explain the strength of a covalent bond based on the extent of overlap. That means the greater the orbital overlap, the stronger will be the covalent bond. The valence atomic orbitals in a molecule are different from those in isolated atoms. This concept is simply known as hybridization. We can enter into more detailed aspects of hybridization in coming slides and in coming modules. First of all, we are entering into the most important aspect of the valence bond theory, that is nothing but orbital overlap and conditions for effective overlap. We already noted the fact that the strength of a covalent bond depends on the extent of overlap between the atomic orbitals. Now we are focusing on the orbital overlap and the conditions that lead to effective overlap. Only effective overlapping can lead to the formation of a stable covalent bond. That's why the condition for effective overlap is highly relevant as far as the orbital overlapping is concerned. Atomic orbital overlap refers to the interaction of atomic orbitals from two different atoms leading to the formation of a covalent bond. This point is very familiar to you. That is, during the formation of a covalent bond, there occur the overlapping of atomic orbitals. It is the partial merging, that is, atomic orbital overlap is the partial merging of atomic orbitals which results in pairing of electrons. The extent of overlap decides the strength of a covalent bond. In general, greater the overlap, stronger is the bond formed between the two atoms. For a strong and stable covalent bond, the overlapping orbitals must meet the following conditions. So, we are discussing the conditions for effective overlap. The first condition for effective overlap is here, that is the proper orientation. Proper orientation is the first necessary condition for effective overlapping between atomic orbitals. The interacting orbitals must align properly for maximum overlap. This is the second condition for effective overlap, that is, the participating atomic orbitals have comparable energy levels. So, comparable energy levels is a necessary condition. The participating orbitals should have similar energy levels for an effective bonding or an effective overlap. This is the third condition for effective overlap, that is same phase interaction. Same phase interaction means the participating atomic orbital must be in same phase. That phase can be represented by using signs that we can enter into more details of which in coming slides. Bond formation occurs when atomic orbitals have same phase. That is, the overlapping will be more effective if and only if all the participating atomic orbitals must be in same phase. This is the next condition for effective overlap, that is optimal distance. What do you mean by the term optimal distance? We are now discussing the condition for effective overlapping between atomic orbitals. So, for an effective overlapping, the participating atomic orbitals must be placed at a suitable or optimal distance. Too much or too little distance, that is high distance or very small distance between atomic orbitals reduces the efficacy or efficiency of overlapping. So, optimal distance is another important condition for effective overlap. Now we are discussing three kind of overlapping, that is nothing but positive, negative and zero overlap. I just mentioned about the various conditions for effective overlapping. In that conditions, we heard about one parameter, that is the participating orbital must be in same phase. Based on the phase of the participating atomic orbitals, we can have three kind of overlapping. They are positive, negative and zero overlap. Now we can enter into details of such positive, negative and zero overlap. When orbitals of two atoms come close to form a bond, their overlap may be positive, negative or zero depending on the sign. Sign represents the phase and direction of orientation of amplitude of orbital wave function in space. This orbital wave function is nothing but a mathematical function. This is associated with the quantum mechanical treatment of the chemical bonding. Every atomic orbital as well as molecular orbital are treated as a wave function in quantum mechanics. That's why the term wave function appeared here. This is for the sake of convenience. You can study more details about the quantum mechanical aspects of the chemical bonding in your higher classes. Now, positive and negative sign on boundary surface diagrams show the sign or phase of orbital wave function and are not related to the charge. It should be noted that whenever you are moving through the representation of the px, py and pz orbitals, you know the p orbital is a dumbbell shaped arrangement. In that dumbbell, you are sometimes putting positive and negative charges. And this statement is about such a charge. Such a charge is not indicating the actual charge. The sign, the positive or negative sign is not an indication of the charge but simply represents the phase. In positive overlap, orbitals forming bond should have same sign or in same phase orientation in space. That is, the positive overlap is obtained by the overlapping between like signs or in phase overlap. In phase overlap is known as positive overlap. This positive overlap can be illustrated by taking two pz orbitals as an example. That is, there occur a positive overlapping between two pz orbitals as shown here. The first pz orbital, as I mentioned, has two lobes. One is represented by negative sign, other is represented by positive sign. Here represents two overlapping, the overlapping between two pz orbital, and it is positive overlap. This is said to be the positive overlap because there occur overlap between like signs. Like sign means the same phase. So positive part overlap with the positive part of the second. That is, there is the overlapping between like signs or overlapping between same phase. Same phase overlap is otherwise called in phase overlap. It is otherwise called the positive overlap, or positive overlap is the synonym of in phase overlap. You can say an overlap is positive only if the overlapping is between like signs or similar phases. Now, we are discussing negative overlap. Negative overlap is otherwise called out of phase overlap. This out of phase overlap between two pz orbital is shown here. Here, the positive part of the first pz orbital overlaps with the negative part of the second pz orbital. That is, it is very well clear that here the overlapping is between opposite signs, or the overlapping orbitals are in opposite phases. Such kind of overlap is termed as out of phase overlap or negative overlap. Another type of overlap is zero overlap. This zero overlap is out of phase and this is due to different orientation direction of approach. We can exemplify the zero overlap by taking the overlap between a px orbital and an s orbital. Here you can say that the px orbital is not in phase or out of phase with the spherically symmetric s orbital. Also, this is the zero overlap between px and py. You know that px orbital oriented along x direction, py orbital is perpendicular to the px orbital, so there is no effective overlap between them. Such an overlap is represented as the zero overlap. Now we are discussing sigma and pi bonds. You are very much familiar with the sigma bond and pi bond, and now we are entering into more details of the sigma and pi bond, their formation, their strength, their stability, etc. The covalent bond may be classified into two types depending on the type of overlapping. They are the sigma bond and the pi bond. First of all, sigma bond. This type of covalent bond is formed by end-to-end or head-on overlap of bonding orbitals along the internuclear axis. Simply we can say like this, a sigma bond is produced by the end-to-end overlapping of atomic orbitals. This end-to-end overlapping is called head-on overlap. Otherwise, it is termed as axial overlap. The term axial overlap is because the overlapping happens along internuclear axis. The orbital overlap and spin pairing to form sigma bond inside some diatomic molecules are shown here. This represents the formation of hydrogen molecule. You know, in the case of the hydrogen atom, the electron is present in oneness orbital. So, in each hydrogen atom, there is a half-filled oneness orbital. They will undergo end-to-end overlap or head-on overlap to form the single bond between two hydrogen atoms, or H2 molecule is formed by this. So, here the overlapping between two half-filled oneness orbital is termed as head-on overlap or end-to-end overlap, and that end-to-end overlap results in the formation of a sigma bond between two hydrogen atoms. Now, this is the representation of the HF molecule. In the HF molecule, you can see the end-to-end overlapping between oneness orbital of hydrogen and 2pz orbital of fluorine. This orbital overlap is strictly end-to-end, and in HF molecule there occur a covalent bond formation that is nothing but the sigma bond. This is end-to-end overlapping in fluorine molecule. During the formation of the fluorine molecule, there occur an end-to-end overlapping between 2pz orbital of first fluorine with the 2pz orbital of second fluorine. Their orientation is along the internuclear axis, and the overlap shown here is end-to-end overlap or head-on overlap, and as a result, in the F2 molecule, the single bond present between two fluorine atoms is strictly the sigma bond. Now, the second type of bond, that is nothing but the pi bond. In the formation of pi bond, the atomic orbitals overlaps in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. That is, the lateral overlap or sidewise overlap is resulting in the formation of pi bonds, or the lateral overlap happens perpendicular to internuclear axis. We can enter into more details of the pi bond formation. The orbitals formed due to sidewise overlapping or lateral overlapping consists of two saucer type charged clouds above and below the plane of the participating atoms, that is shown here. This is the pictorial representation of the orbital overlapping, that is sidewise or lateral overlapping. The upper part of the first p orbital overlaps with the upper part of second p orbital. That overlap is termed as sidewise or lateral overlap, and the lateral overlap leads to the formation of the pi bond. Now, pi bond can be illustrated by considering the formation of oxygen molecule. When the half-filled 2pz orbitals of two oxygen atom overlaps along the z axis, considering z axis as the internuclear axis or molecular axis, a sigma bond is obtained. In addition to the sigma bond, there occur the formation of a pi bond also. The other two half-filled 2pi orbitals of each oxygen overlap laterally or sidewise to form a pi covalent bond. That is, in O2 molecule, one bond is sigma bond, that is formed by the end-to-end overlap of 2pz orbitals of each oxygen, and the second bond is the pi bond, which occur due to the lateral or sidewise overlap of 2px orbitals of each oxygen. Now we are discussing strength of sigma and pi bond. It should be noted that the sigma bond and pi bond are formed by two different kind of overlaps. Sigma bond is formed by end-to-end overlap, and pi bond is formed by lateral or sidewise overlap. Since the overlapping is different, their strength is also different. The strength of a bond depends on extent of overlapping. In the case of sigma bonds, the overlapping atomic orbitals takes place to a larger extent. That is, extent of overlapping is high when the overlapping is end-to-end. That is, during the formation of a sigma bond, there occur a large extent of overlapping. That means the sigma bond is stronger as compared to pi bond, where the extent of overlapping occurs to a minimum extent or a smaller extent. This point is highly important as far as strength of sigma and pi bonds are concerned. Sigma bonds are formed by end-to-end overlap, which is a greater overlap, or the extent of overlap is high, and sigma bonds are more stronger than the pi bonds. Now we are discussing bond characteristics or bond features. The valence bond theory can be used to explain the nature of different type of bonds such as sigma bonds, pi bonds, etc. That is, we can explain the nature of sigma bond as well as phi bond and their characteristic features based on the principles of the valence bond theory. Sigma bonds involve end-to-end overlap of atomic orbitals, while pi bonds involve sidewise or lateral overlap of p orbitals. Now, directionality is important aspect of the valence bond theory. The valence bond theory emphasizes the directional nature of covalent bonds. It should be noted that the covalent bond is directional. That is, in space they have a specific orientation. This directional property of the covalent bond enable definite shape to the covalent molecules. For example, methane is a tetrahedral molecule, water is a bent molecule, HCl is a linear molecule. All these geometries or structure is as a result of the directional properties of the covalent bond. And the valence bond theory emphasizes the directional nature of the covalent bonds. The VB theory explains why certain molecules have specific shapes and bond angles based on the orientation of the atomic orbitals involved in bonding as well as hybridization. Now we are focusing another important aspect which is associated with the valence bond theory. That is nothing but hybridization. Valence bond theory introduced the concept of hybridization, which involves the mixing of atomic orbitals to form hybrid orbitals. In your school classes, you learned about the concept of hybridization. By definition, hybridization is defined as the mixing up of atomic orbitals of nearly same energy to get a set of orbitals having identical energy and shape. This hybridization is one of the most important aspects of the valence bond theory. Linus Pauling proposed that valence atomic orbitals in the molecule are different from those in isolated atoms. That is, when atoms are converted to molecules, there occurs some change in valence atomic orbitals. The number of hybrid orbitals obtained equal to the number of atomic orbitals mixed. This is a very significant feature of hybridization. Number of orbital take part in hybridization is equal to number of hybrid orbital produced. For instance, in sp hybridization, there occur the intermixing of one s orbital and p orbital, that is, two orbitals are take part in sp hybridization, and as a result you will get two sp hybrid orbitals. That's why we can say that the number of hybrid orbitals is equal to number of orbitals take part in hybridization. The type of hybrid orbitals obtained varies with the type of atomic orbitals mixed. There are several types of hybridization. We can enter into more details of hybridization and the geometry of the molecules, etc. in some other modules. Types of hybridization. There are different kinds of hybridization. For instance, sp, sp2, sp3d, sp3d2, sp3d3, etc. are very common type of hybridizations in simple molecules and ions. As the name indicates, in the last one, sp3d3 hybridization, one s orbital, 3 p orbital and 3 d orbitals undergo mixing up. that is 7 orbitals undergo mixing up, and as a result 7 hybrid orbitals are produced. So this point, the number of hybrid orbital produced is equal to number of atomic orbital take part in hybridization is a significant feature of hybridization, and the concept of hybridization is a core aspect of the valence bond. Formation of hydrogen molecule. You know, hydrogen molecule is the simplest molecule with the existence of a covalent bond. During the formation of hydrogen bond, there occur the overlapping of atomic orbitals, and now we are discussing the formation of hydrogen molecule with respect to the valence bond theory. Valence bond theory provides a detailed and insightful treatment of the hydrogen molecule formation, explaining how two hydrogen atoms bonded to form a dihydrogen molecule. Let us consider the formation of a bond between two hydrogen atoms to form H2. When two hydrogen atoms come close together, new attractive and repulsive forces begin to operate. What are the attractive forces? The force of attraction between electron of first hydrogen atom with the nucleus of the second belongs to attractive force. Another attractive force is the force between electron of second hydrogen with the nucleus of the first. There occur repulsive force also. The first repulsive force is this force between nucleus of two hydrogen atoms. You know, the nucleus is a positively charged body. When two same positively charged nucleus come together, there occurs some repulsive force. The second repulsive force is the force between electrons of two hydrogen atoms. So there occur some attractive force as well as some repulsive force during the formation of hydrogen molecule from two hydrogen atoms. Attractive force tended to bring two atoms close to each other, whereas the repulsive force tended to push them apart. Experimentally, it has been found that the magnitude of the new attractive force is more than the new repulsive force. As a result, two atoms approach each other and potential energy of the entire system decreases. As the two atoms come more closer, the potential energy reaches a minimum value. And at this minimum potential energy stage, two hydrogen atoms bonded together to form a stable molecule with a bond length of 0.74 angstrom. If the two nuclei come too close, stronger repulsive force begin to dominate, which leads to increase in the potential energy significantly. That is, at a minimum potential energy, there occur bond formation with a bond length of 0.74 angstrom between two hydrogen atoms. Now you imagine if the two hydrogen atoms are more closer than this distance of 0.74, then the repulsive force starts dominating, repulsion starts dominating, and the potential energy of the system increases. This formation of hydrogen molecule and the potential energy can be represented by using a potential energy diagram. Here the y-axis represents the potential energy and x-axis represents the internuclear distance. As I mentioned, when the two atoms are at infinite distance, there occur no interaction or no overlap between them. When they come close together, some attractive as well as repulsive forces come to play. And at this point of 0.74 angstrom, there occur some minimum potential energy due to greater attraction. At this point, there occur the formation of the covalent bond happens between two hydrogen atoms. And if the two hydrogen atoms will more closer than 0.74 angstrom, then the potential energy of the system decreases. So this curve represents the potential energy diagram corresponds to the formation of hydrogen molecule from two hydrogen atoms. The curve starts at high potential energy, that represents atoms which are far apart, decreases to a minimum distance at which point the bond formation happens, and rises steeply as the repulsion dominates at a very short distance. At the stage of minimum potential energy, two hydrogen atoms bonded together to form a stable hydrogen molecule. Since the energy gets released when the bond is formed, the hydrogen molecule is more stable than that of isolated hydrogen atoms. The energy so released is called bond enthalpy. The bond enthalpy associated during the formation of hydrogen molecule can be represented by this expression. 2H gas gives H2 gas, delta H is equal to minus 436 kilojoule per mole. And it should be noted that during the formation of 1 mole of hydrogen from 2 hydrogen atoms in the gaseous state, the amount of energy liberated is 436 kilojoule. Conversely, 436 kilojoule of energy is required to dissociate 1 mole of hydrogen molecule into 2 mole hydrogen atoms. That is, bond formation is an energy liberating process and bond dissociation or bond breaking is an energy absorbing process. Now we are discussing concept of resonance. This is the last part of the present module. Valence bond theory can also describe resonance structures which occur when there are multiple valid ways to represent the distribution of electrons in a molecule. Before entering into detailed aspect of this, we have to first define resonance. What do you mean by the term resonance? Resonance occurs when the structure of a molecule cannot be shown by a single structure, but more than one structure is required. That situation is termed as resonance, and the individual structures are called canonical structures or resonating structures. The concept of resonance is very important as far as the valence bond theory is concerned. Resonance structures are a fundamental concept in understanding the electronic structure of molecules with delocalized electrons. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid which describes molecule accurately. These statements describe every aspect associated with the resonance. Now we are discussing the resonance with an example, that is, we are showing the resonance in ozone molecule. Ozone molecule is a triatomic molecule. The two important resonating structures of ozone are shown in the first row, that is, in the first structure, left hand side there is a single bond, in the right part there is a double bond. Conversely, in the opposite resonating structure, in the next resonating structure, the first part is a double bond and the second part is a single bond. So, the first and second are two resonating structure or canonical structure of ozone molecule. And the original ozone molecule can be considered as a resonance hybrid of first and second structure. That is, in between these oxygen atoms, there occur partial double bond character. So, structure 3 is the resonance hybrid of first resonating structure and second resonating structure. So, the actual ozone molecule can be considered as a resonance hybrid of these two resonating structures. Structure 1 and structure 2 represent two canonical or resonating structures, while the structure 3 is the resonance hybrid, that is the actual molecule. Now, resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. I previously mentioned the fact that actual ozone molecule is a resonance hybrid of first and second resonating structure. The resonance hybrid always have lesser energy than individual canonical structure, and hence the actual molecule is stable than each and every canonical structure. That all about the present module. Have a nice learning experience. Thank you.